Hello? Oh, sweet. Okay. Hey guys. Thanks for the wonderful introduction. My name is Jerry. I'm co-founder and CEO of LlamaIndex. And today the talk will be practical data considerations for building production-ready LLM applications. LlamaIndex, by the way, is an open source framework for building LLM apps over your data. We came up with the name the week before Meta released their model, so I just want to point that out. I feel like I have to point that out at every talk I go to. Anyhow, let's talk about retrieval augmented generation. How many of you guys know what retrieval augmented generation is? I'll give a show of hands. Okay, sweet, that's basically everybody. Awesome, okay. So we call it RAG for short. And the overall context here is that LLMs are a phenomenal piece of technology for knowledge generation and reasoning. They're pre-trained on large amounts of publicly available data, but it turns out they can actually reason over new information as well. And you can use them to answer questions, summarize stuff, like generate a bunch of texts, like plan out stuff, automate your workflows. And I think the key question here is just, how do you best augment language models with our own private data? If you've been to basically some of our previous talks, these are basically the two slides that we start with, but that really is the mission statement of the company, is to figure out how do you unleash the capabilities of LLMs with all the reasoning power on top of data that that it hasn't been trained over. So a brief note on LlamaIndex is it's a data framework for LLM apps. It's a data management and query engine for your LLM application. So we offer a very robust production-ready toolkit across the data lifecycle of data ingestion, data indexing, and being able to actually query over your data. So we have like over 100 different data loaders from unstructured to structured file formats through LlamaHub, which is a community-driven kind of like data loader hub. Once you actually load in this data, we have a robust suite of tools to do a bunch of transformations on this data. So you can split the data, parse it, add metadata to it, add a bunch of, add embeddings to it too, and add other stuff so that, like, in the end, it's basically a new type of ETL pipeline that you want to store in your vector DB. We also integrate with vector databases. We have like 30 plus integrations, but we also have integrations with other storage providers, from graph databases to document stores as well. And then in terms of the data, like once the data is actually in your storage system, then you want to do stuff like retrieval, querying, synthesis, all these things with the LLM over it. And so this ranges from stuff like question answering, summarization, agents, and more. Okay, and so I'll kind of, this is just like a brief overview of LlamaIndex. The formatting's a little messed up here, but basically the idea is that you can basically set up a QA system over your data in about 3 lines of code, right? And so the advantage of LlamaIndex, one of the advantages is that it has a very high-level API, if you want it to be, so that you can basically make it very easy to load in a bunch of documents. That's the first line right here. Index a bunch of documents, and then basically ask questions over it without you really having to worry about the complexity. And of course, we have the underlying lower-level abstraction so that if you are an advanced user that wants to go in and customize things, you can, and you absolutely should. And in fact, that's pretty much the topic of this talk, is how should you iterate on your retrieval algorithm and your synthesis to actually create more performant RAG applications. Because this thing, I mean, look, like this thing right here takes you like 10 minutes to set up, right? Like without really needing to understand a bunch of stuff. So what are the downsides here, and how can you iterate on that to fix retrieval and generation issues? So we'll talk about what I call kind of like the naive RAG stack for building a QA system. And as I mentioned, it's about 5 lines of code. It's 2 main components. There's data ingestion and parsing, and then also data querying. So data ingestion means that you load in some documents, right? And let's say you just use a pretty simple PDF parser, like PyPDF, or there's like 10 plus integrations available on LlamaHub. Once you take in these like documents, you then chunk it up into a set of even chunks. So you split it, say, by sentences or by like tokens, and you do like every 1,000 words or every like 20 sentences or something. But you basically have a bunch of chunks, right? And each chunk is just a piece of raw text. And then you just dump the chunks into a vector database along with an embedding. And that embedding is generated by an embedding model like OpenAI. Once that is in the database, then you want to query over that data. So you want to fetch the top k most similar chunks from the vector database and plug this into your LLM response synthesis module. So I think if you've actually tried building this, if you have actually just tried doing the 5 lines of code in LlamaIndex, like inevitably you're going to run into failure modes, especially as you scale to larger numbers of documents, as you scale to a diverse set of documents, as you scale to more complex document types. If a PDF has like a bunch of embedded tables, if you have like a markdown file with a bunch of sections. And so in terms of failure modes, there's basically two main categories. There's quality-related stuff like hallucination and accuracy. And there's also stuff I would say is like kind of more non-quality related, like system-level considerations like latency, cost, and syncing. So from talking to a bunch of users who are just building LLM apps of your data, like and RAG pipelines, the most common reason for bad response quality is bad retrieval. If the retrieve results are bad, there's just no way that the LLM can actually synthesize a proper response without hallucinating. And so digging into this a little bit more, what does bad retrieval really mean? It can mean a few different things. One is low precision. So not all the chunks in the retrieve set are actually relevant. I mean, some of them might be relevant, but not all of them are. And what this means is you have a bunch of irrelevant context you're feeding into the language model, which is ripe for hallucination, synthesizing stuff that's not actually relevant to your question, and also getting into lost in the middle problems, where the longer the context is, counterintuitively, the language model actually has a harder time picking out stuff in the middle to the relevant piece of information. There's also low recall. Not all the relevant chunks are actually retrieved. So if you're actually missing crucial context, this means that your LLM doesn't have enough context to synthesize a proper answer. There's outdated information as well, like the data is redundant or out of date. So stuff that's not response quality related includes the following. How do you deal with updates in like the source document? How do you, if like your PDFs actually change or you have new Slack conversations and you're using that as a data loader, how do you propagate these updates into your downstream vector store, which contain like the chunks of the original text? And then system-wide, how do you ingest hundreds and thousands of documents in a scalable, robust way? So I've kind of like touched on this topic, but it's always evolving. But like part of the key lesson here is you should always just think carefully about the way you define data and how data actually influences the quality of your LLM application. And in that sense, it's not really that different than your traditional MLOps pipeline, where again, like data engineering matters quite a bit to actually improve the performance. So the bulk of this talk is basically talking about some general techniques for better performing RAG beyond kind of maybe what you've seen that you can do in like 5 lines of code from LlamaIndex or LangChain or other frameworks. So, and we'll try to give examples for each one on like failure modes, and I'm also happy to answer some questions at the end. One is, so when you take these chunks, by default, you kind of embed these chunks, right? You just generate an embedding over the raw text chunks, and you store in a vector database. And these same chunks are used for both retrieval and synthesis. And so the main issue is that when you just embed the raw text chunks, they can basically bias your embedding representation with a bunch of filler content. I've said this a few times, but I think this original idea was also brought up by Max from Sid.ai, so, and then this slide was taken from that. So giving credit to him for bringing up this great idea. It's like, if you have like, let's say you're embedding an email, right? That email is gonna have a ton of filler words, like hi and sincerely and looking forward to it. That stuff, depending on your embedding model, is gonna bias a semantic representation. And so if there's a way for you to somehow just extract out the salient bits of information that are actually relevant to the question that you want to ask, how can we do that? So one basic idea here, and this is just a very simple trick that I'd encourage all of you guys to just try out and see if it works, is you embed the text at a smaller level than the level that you synthesize over. So if you embed the text at the sentence level and dump a bunch of sentence chunks into a vector database, okay, then you have more granular chunks that you can retrieve over. And then you do like top K retrieval, okay, over these like sentence chunks, and then you'll just retrieve individual sentences. But what you do before these chunks actually hit the LLM is you then expand the context, right, around that window, around the sentence. So you need like proper metadata representations for this to work well. But the key idea here is that you kind of like, it's kind of like a win-win for both the retrieval and synthesis side. If there's too much filler content on the retrieval, then your retrieval might be bad. So if you're retrieving giant text chunks, it might not be great for kind of fetching relevant context, and you get lost in the middle problems. But then once you actually retrieve the relevant pieces, you want enough context for a language model to actually synthesize an answer. And so this is a way around that. We tried this with some basic experiments. With sentence window retrieval, this is what we're calling it with k equals 2, you can actually get back an informative answer over this climate change report that we ran over. But when we set k equals 5 over kind of using a more naive retrieval method with bigger chunk sizes, you realize that the actual answer is somewhere in the middle, but it also retrieves a bunch of irrelevant context. So there's 4 chunks that are irrelevant and 1 chunk that is relevant. And then you get in these lost in the middle problems. And then the LLM, like especially if it's like a crappier LLM, like GPT 3.5 versus GPT 4, it's not able to synthesize an answer for you. Another general idea that I think has worked well for us, but I urge all of you guys to give it a try and let us know your feedback, is to try embedding like a reference to the actual text chunk instead of the text chunk directly. And so examples of what are references, right? It could be literally anything, but the idea is, again, in the spirit of decoupling embeddings from retrieval and synthesis, it could be a smaller chunk if your original chunk is very big. It could be an extracted summary. It could be a set of LLM-generated questions that you might want to ask the chunk. So like hallucinated questions given the chunk itself. So you want to retrieve those references first, and then once you actually retrieve those, then link to the actual text chunks that, again, goes into the language model during synthesis. We tried this on a few kind of basic experiments. And so the base retriever is like naive retrieval. And we tried both kind of like chunk-based references with like extracted summaries, and also metadata references with kind of like extracted like structured information. And in both cases, when you actually retrieve those instead of the raw text chunks, you get better retrieval performance, which then in turn leads to better generation. The next concept here is this idea of organizing your data for more structured retrieval. And so this is the idea of injecting metadata or structured information into your document. So the thing with metadata is, imagine you have like just a raw like text chunk here, right? And this is just a random snippet from the GPT-4 paper. Metadata is basically just a JSON dictionary that you attach on top. And the thing about metadata is that it's useful for both retrieval, right? It can help retrieval, as I basically just showed here. It can also just help synthesis. It can add more context so the language model kind of understands what's going on at a higher level. And the other thing is that it directly plugs into your vector database like metadata filters. These days, all the major vector DBs, so Chroma, Pinecone, Weaviate, Quadrant, Milvus, and all the other ones, they all support some aspect of structured filtering, and so that you can directly query for both structured information as well as semantic queries. Examples of metadata include things that you would define yourself, things that are part of like common like data parsers, like PDF parsers, and also things that LLMs can probably extract for you. And so these include stuff like page numbers, document titles. It could be even more creative, like a summary of adjacent chunks. This is something you can use an LLM for. Or even questions that a chunk can answer. If you're familiar with like hide, which hallucinates an answer given a question, this is kind of like reverse hide. Given like a chunk of context, hallucinate a bunch of questions that can answer that can be answered by the context. And we found, we're still kind of experimenting with like the very best practices for this, but we have found in a lot of cases, on a more case-by-case basis, some of these techniques can basically help your use cases. So a very simple use case here is that you can, for instance, like add page numbers as metadata. Once you have page numbers in the metadata, and assuming the metadata actually gets injected as text, then you can basically kind of get inline citations over your answers, right? Because when the LLM sees a bunch of text and it has the the page numbers associated with the text, then it can actually give you kind of inline citations. Like here, it's giving an answer in bullet points, and it has like parentheses, page 6, page 6, page 18 over here. Here's just, I don't know if you guys can see this kind of, but this is just an example of like a text chunk. And everything here in this top half, like before this, like these dashed lines, are metadata. So there's stuff like page label, file name, document title, questions this excerpt can answer. And then this is the actual text chunk itself. And so what you get is your final chunk representation looks something like this, where it's like structured information, dash, dash, and then like unstructured information. Some of this stuff, again, is kind of manually defined or through a parser. Some of this can be extracted with an LLM, like what is Uber Technologies' definition of adjusted EBITDA. So it's kind of up to you. There are downsides to adding too much metadata. One, it makes your retrieval a bit slower. And then two, it can actually kind of hurt your performance if you just dump too much metadata, so it's hard to disambiguate between different chunks. But it's just like a tool in your toolkit that you can use. Elaborating on that last bit of how this can actually plug into kind of the vector DB, right? How you can actually take this metadata and plug it into, integrate with vector database like metadata filtering is, imagine you have like some basic question. Like, can you tell me about Google's like R&D initiatives from 2020 to 2023? And assume like, there was some parser that's able to take the set of like financial statements for Google, and then actually kind of like the 10Ks, for instance, and then actually tag it with each year. Now, if you don't take advantage of that at all, and then you just dump all the 10K document chunks into a single collection, and you just do like, say, top 4 retrieval, you're just gonna get like a random mess. Like chances are you're not actually gonna get like specifically the, each year, the relevant context. So you might get 2 from 2020, you might get 2 from 2022, you might get none for like 2023. And so there's no guarantee you'll actually return the relevant text chunks purely with semantic search. It's just a little bit fickle that way. But let's say you actually tag the documents with metadata filters, right? You use metadata, attach the year to each document. And then you actually store this in, say, like Pinecone or something with like the documents with the year itself. So when you ask a question, you can, one trick you can do is you can actually have the language model not just like pass along this question, but actually infer the set of metadata filters, right, that it might need to ask to actually query this database effectively. And so ideally, right, in this setting, the language model can actually infer that, hey, like, the set of metadata filters that I want is from specifically like, range 2020 to 2023, and identify those specific documents and retrieve the relevant chunks of text. And so it helps to narrow down the candidate set to something that's a lot more precise, and then that's something that can basically help your retrieval. The next idea that I think I've kind of been like becoming a bigger and bigger fan of, because I think it's actually pretty general, and I'm noticing the diagram kind of cuts off here, but the idea here is like this idea of hierarchical or recursive retrieval. A lot of times your data representations are not flat. There is kind of some aspect of like a hierarchy or a relationship between them. If you have a bunch of documents, let's say you have like 100 PDFs, you can like separate group them by like category, and then within each document, like a document could be very long, you can represent each document by its summary. A lot of times when you do retrieval, it helps to retrieve stuff at the top level first before just like directly trying to fetch the relevant chunks. So for instance, if you model documents first by their summaries, retrieve based on that, and then you go down into the relevant chunks, that can oftentimes get you more relevant context than actually fetching the specific document chunks directly. Another aspect here is a lot of PDFs, right, have like embedded tables and graphs and a bunch of other stuff. So how do you actually model this appropriately? And we've been kind of thinking about this a lot, and it turns out like, if you like represent each embedded object as its own kind of entity, right, and maybe like you vectorize it or have some way of like querying that embedded object, you can stitch things together in some sort of graph, and then you can basically recursively query, start at the top level, find whether or not this embedded object is actually relevant to the query, and if it is, then go down and actually call the query on the embedded object. So elaborating on this first aspect a little bit more, I think one thing we're actively doing is just, for all these techniques, it's like large-scale retrieval benchmarking and kind of evaluation just to make sure that it actually works well. I'll have a bit on retrieval evaluation so that you can, for yourself, validate whether or not this actually works. But in the meantime, the idea is for each document, just extract out a summary, embed the summaries first. And then when you actually kind of like ask a question, maybe fetch the relevant set of documents before going into the documents and fetching the relevant chunks. This could be like a simple but effective technique to make sure you're actually fetching context. So it's like global context to coarse context. And kind of similar to what I described, if you have like, like a bunch of tables, like graphs, or even related documents within a PDF, like if an archive paper has like related works, how do you model this in some sort of graph, right? The embedded objects in a graph. So then when you run a query, you start off at the top level nodes, each corresponding to maybe a sub-object, retrieve the nodes, and then go down and actually try retrieving the sub-objects. And it's interesting. I think we have like a few kind of qualitative analyses showing that if you just do the naive like text splitting thing, a lot of times you just can't parse like tables, right? It just doesn't work at all. And kind of embedding search has a pretty, it's pretty bad at just being able to parse out relevant information from like a random like dumped table within a document. But this might warrant like a more structured approach like this. Cool. Okay, I'm actually doing pretty good on time. I think in the last like 3 minutes or so, I'll talk a little bit about evaluation. So maybe this is just a kind of, I think I have one slide here, but the idea is how exactly do you evaluate retrieval? I actually think evaluating retrieval is pretty important if you want to evaluate like LLM stuff in general. I feel like it's something that people don't quite talk about as much as just like measuring the generated response quality and hallucination and using like LLMs to parse the response. But like the retrieval itself is not really like a new problem. It's something that's kind of existed in information retrieval recommender systems for a while. But the interesting thing with LLMs is that they can basically help you generate a synthetic data set. And the better LLMs get, the better the data set that you can benchmark on can be, and then you don't actually need a human in the loop to actually generate this data set. So the way this works is that if you want to generate a retrieval data set, okay, take your documents and similar to RAG, just like parse and chunk it up. Now for each chunk, prompt GPT-4 to generate like a set of questions from each chunk or each set of chunks. Now you have question chunk pairs, right? And that's basically your ground truth. Because given a question, you know what the ground truth context should be because you just generated a question from that chunk using like GPT-4. So then when you run through your retrieval system on your entire corpus, you can basically measure where in that ranking of retrieve results is that ground truth chunk, and then use like traditional ranking metrics. And this becomes kind of like an ML ranking problem. You can use like NDCG, like MRR, a bunch of this stuff to actually measure the performance of it. So I think when we evaluated this, like this is basically what we did. You can see the MRR performance. Notice all the numbers are kind of low. I can talk a little bit about that. Turns out a lot of like generated questions become kind of actually irrelevant, and so that's kind of like a separate challenge. Like you do have to make sure that like when you generate these questions, they're not just asking about like random things, but also like specifically about stuff that can be answered by the context. But that aside, I think it's a very powerful approach that basically kind of automates away the need for human curated data sets. The last bit I'll probably touch on a little bit. I don't think we'll have time to talk about like document updates, but in terms of like addressing scalability challenges, is that yeah, I mean I think like and this is where Ray comes in and can be actually really helpful. Like if you've ever built like a RAG pipeline, it's actually quite slow. If you basically just use kind of out of the box, and I readily admit this, right? Like LlamaIndex or LangChain over like 10 PDFs or something. Especially if those PDFs are pretty big, it can take a while to actually load in all this data, like parse and chunk this data and embed this data. I remember when I was working with Amog on this on the blog post, we tried indexing like the Ray documentation, which had like hundreds of files, and it took like 20, 30 minutes if like you just kind of did it naively, which was like surprising to me, right? And it might be because of like the embedding model, it might be because of like the parsing algorithm, but like this is actually something Ray can actually help a lot with. We basically got a 10x improvement by just like using Ray with different parts of LlamaIndex. Just like massively parallelize a lot of these operations. Parsing across a bunch of documents can be parallelized. Embedding can absolutely be parallelized. Loading into like a vector database can be parallelized. And so if you can just like figure out the right chunks to parallelize, you can massively speed up ingestion. And if you are interested in this, you should check out our blog post. Quick call out, we have a full workshop with Simon, my co-founder and CTO, along with Amog and Goku on Wednesday. I think it's like a 3-hour workshop or something. And so basically a lot of these concepts I just talked about, you'll actually learn how to implement them and then have evaluation in the loop so that you can pretty much validate whether or not this is something that is actually useful to help you iterate on your RAG system and improve it. And so it's actually really, really comprehensive. We obviously, we have Ray at every step to help you like speed up stuff and also help you deploy the final thing at the end. But it's everything from prototype to production. And at the end of the day, that's basically what LlamaIndex is focused on. We don't want you to just build the easy stuff in 5 lines of code. we want you to really iterate on, improve the retrieval system, and create something production quality. And I think that's it. Thank you.
We can probably have 2 questions. Please raise your hand and I keep.
Thank you. I have a question. In your experience, like are GPT-4 models and so on, do they have the capabilities to answer if they're providing the right chunks, or you also potentially need to fine-tune the LLM synthesizer too? Sorry,
was the question whether you need to fine-tune the LLM for?
Yeah, my question is like, do they have capabilities built in and then they just need the right context? Or in your experience, you also think that it's sometimes needed to fine-tune the LLM synthesizer too?
Yeah, that's a good question. I have like an entire separate talk on fine-tuning. I think it's something we're actively trying to figure out right now. I will say for GPT-4, GPT-4 is probably like the gold standard of LLM models these days. And so actually, we haven't really tried fine-tuning GPT-4. I know OpenAI definitely has. But what we have done is use GPT-4 as ground truth to fine-tune like a weaker model, like Llama 2 or GPT 3.5. And it turns out that actually does pretty well. You can have, if you fine-tune Llama 2 or GPT 3.5 on like the chain of thought reasoning of GPT-4, on its ability to write text to SQL, on its ability to generate like coherent responses given context, it actually works pretty well. And so I would definitely encourage you to do that if you're using a cheaper model.
I have a question about, this all sounds good, but the issue is context window size.
Mm-hmm.
So, some of the models like Llama 2, for example, only have a 4K tokens, right? That's not a lot. And by the time you add this metadata, you can maybe get 2 or 3 documents at most in there. How do you handle the limitations of the context window size?
So that's a great question. I think that's precisely the trade-off of metadata if you inject it into the text itself. And so I think for when you inject it into the text, there's really 2 ways you can use metadata. You can use it for embedding-based retrieval, or you can use it for LLM synthesis. And with LlamaIndex, you can actually control whether or not the metadata as a structured dictionary actually gets injected during embedding time or during synthesis time. And so if you're really worried about like limited context windows, and again, it makes retrieval a little bit slower too, you could just not put the metadata into the text itself during generation time, but you could still use it for metadata filtering, right, for vector databases and stuff. So there's ways that you can use it without stuffing the context window. Yeah.
Quick question on RAG. So when you're retrieving information from VectorDB, are you guys doing any optimization on that? Because I've seen that most of the naive solutions, they only do use KNN.
Yeah, I guess all these are optimizations, but these are pretty much like, I'll try to send the slides as well. I think like the idea here is pretty much every technique mentioned is on like a single page in our docs called like kind of techniques you can try to create like more performant RAG beyond just like standard top K. And so there's like, I guess the idea is there's like the data representations, there's like the retrieval algorithm itself. It could be top K, it could be using metadata filters, it could be using hybrid search. And then it's also the way you like kind of organize and structure the retrieval algorithm. So it's like all these things that you can do to try to optimize beyond the existing approaches.
So we're gonna take the rest of the question offline. So thank you very much, Sherry, for very insightful presentations. Please give another round of applause for Sherry.
Thank you.